Okay. So we start. Welcome back to the last lecture. So an order one fraction of the audience is made up by the organizers, but okay. So what I'm gonna say today was to basically finish the discussion of the post-inflationary scenario, where, as we said last time, the heating temperature, so the maximum temperature during inflation, was larger than V, the scale of Pachinko symmetry breaking, and or the Hubble scale during inflation was larger than the scale of Pachinko symmetry breaking V. And we said last time that because of basically the Pachinko phase transition or quantum fluctuations during inflation, in this post-inflation scenario, the axion field has inhomogeneities on microscopic scale, if you want, on line scales that are much smaller than the Hubble horizon today. And we said that if we could discuss the axion as only made of a bunch of waves, then in any case, all the momenta that are smaller than, that are larger than the inverse Hubble scale at the time H star, this famous H star, then in principle, all the fluctuations will smooth out over the scales, and we will remain with a constant field over H star, over patches of order H star. However, turns out that the story is a bit more complicated. So if it were the case, then I could do the average of all the possible misaligned angles, because I could just take the average of quote-unquote misaligned mechanism that we saw last time over each patch, and I could just use the formula we saw before with that value of theta 0, just because in our big universe you would see all the values of theta 0, and so you have to average over them. However, as we said, this story is a bit more complicated because of the fact that the axion has also topological effects in it. So just to mention, so in this scenario, in principle, there's no free parameters, so in the initial conditions, just because the axion is random. So in the previous scenario, we had the value of theta 0 that was not chosen, so there was a cosmographical property. So in our Hubble patch, the theta 0 would be some value, some other Hubble patch, another value. And so this parameter is basically free, and therefore the previous scenario was unpredictable. In this one, the axion basically does not have any free parameter, because it has these random fluctuations, and therefore in this scenario is predictive, meaning that there's in principle a unique value of Fa, such that, like you see, the axion makes up the correct, so omega A is equal to omega dark matter, which is 0.25, okay, around 0.25. So there's a unique value of this Fa. So there's a unique value of the axion mass, which means that we can in principle calculate it and go in an experiment and find it, if it's the case. So, however, as we will discuss in this lecture, the calculation is not very easy, and that's basically still open field of research in which I'm involved. So I'm happy to talk about this because I'm involved in this. So also I want to say that you ask questions, because this stuff starts to become a bit complicated or technical. There's also jargon, so as soon as I say some jargon, stop me and ask me what I mean, because okay, so the idea is that so in terms of a plot, if you want, we saw there's a plot GA gamma gamma as a function of MA yesterday. There was a pre-inflationary scenario that was predicting a large number of a large range of MA between, let's say, 10 to the minus 12 EV to 10 to the minus 3 EV. In principle, we will see that there will be a unique value around here on the upper part of this plot, for which the post-inflation scenario will give me the correct dark matter. While the pre-inflation scenario, I could choose basically any value of theta 0, which gives me the correct dark matter balance in all this range. Okay, so the problem of the post-inflation scenario is that besides these fluctuations of the axion field, which are there after the Pachinko symmetry transition, the field also has generically configurations where it wraps non-trivially in space the fundamental domain 0 to pi, or minus pi and pi v. So in principle, sorry, 0 to pi v. So in principle, I can find a field configuration where I start from 0, and then I go around all the way to pi v, and then I go back to pi v, but 2 pi v is 0 itself, because the Pechequin field was periodic, okay, the axion was a phase of this Pechequin field. So I can find a configuration of this kind, and the configuration, this will be the axion, okay, the component of the Pechequin field, the angular component. See, however, this configuration is singular, because in principle, by continuity, I can contract this configuration into a point. So I can just continuity contract this configuration like visually to a point, and there will be one point inside this circle, no, or this kind of circle, this loop, where the axiom, where this angular variable basically assumes all the values between 0 and 2 pi v. No, in principle, it assumes all the value, so in principle, this is not very well defined. Okay, and if you do the same reasoning in all space, there will be a line of point where this happens. Okay, and this configuration is called axion string. So axion string. And now I will explicitly show a configuration, an explicit example. But the idea is that there is a line of points in space such that if I go around the angular variable of the Pechequin field wraps non-trivially. These are also called a topological vortex, or also known as global vortex. Global vortex. Okay, this is a well-known configuration in theories where you have a U1 global symmetries that are spontaneously broken, like the Pechequin symmetry. And just to give you an idea of how these vortices arise and why they arise, I just show you a simple field configuration where this happens. So I consider my KSVZ model where I put to 0 the fermions. So I consider KSVZ where I put to 0 the fermions. So the Q I put to 0, and this is self-consistent. So these are heavy quarks, and this is self-consistent with the equations of motion. Okay, and the idea is that okay, KSVZ model I had the Lagrangian of the kind. Okay, I just write the relevant pieces. This is d mu phi modulo square. You remember it was a complex scalar field with Mexican potential, and then I have my Mexican potential lambda over 4 phi modulo square minus v square over 2 square. Okay, this lambda over 4 I can also write in terms of the mass of the corresponding ideal mode. Remember, mr squared over 2v squared. Okay, there's a relation between lambda over 4 and mr squared over 2v squared. Okay, and remember that the FA was related to V in the following way. V is basically FA modulo the number of these heavy quarks. V is in fact n times FA. It's the number of the heavy quarks that carry the Pechequin charge. So in principle here I also have to add the axion potential V of A, which is a function of A and so on. But at high temperatures I can neglect this. So if I am at temperature around the Pechequin phase transition, I can neglect this axion potential and only consider this one. So my statement is that there exist field configurations of this Pechequin field phi is written, okay, as you know, in terms of the radial mode, no, and of the on the axion this way. So this was what we saw last time. So the equation of motion admit topological and consider configurations that look like axion strings, and to see how they look, at least the straight strings that are straight along the z direction. What I do, I write this equation of motion, the equation of motion of this Lagrangian in I try to find t independent and z independent solutions of the equation of motion of the Lagrangian, and and therefore you have and with some cylindrical symmetry. So if I write this equation of motion in terms of the equation of motion with with these assumptions, plus I write the gradients in terms of cylindrical coordinates. What I find that the equation of motion, okay, you can derive them. They're like 1 over r tilde divided by the derivative with respect to r tilde. Now this r tilde basically r times r tilde, the derivative with respect to r tilde of phi. So this is then I have 1 plus 1 over r tilde square, the derivative with respect to theta, okay, square. Then I have phi. So this is basically my Laplacian written in cylindrical coordinates. And I have something like 1 over v square phi modulus square minus v square over 2 equal to 0. So these are my equation of motion written in cylindrical coordinates, where this r tilde is basically r normalized by the mass of the radial mode. R tilde is equal to r times the mass of the radial mode. Okay, this you can show that this is the case. So this is the Laplacian. This will be the, okay, I'm basically doing like this, so x and y, and then r will be the distance with respect to x and y, and theta will be this angular. Okay. MR is a free parameter. So in the radial mode, MR has a mass of order, okay, you see there, of order v times the square root of lambda. So here I'm kind of assuming that lambda is maybe, okay, lambda is whatever, but for now I'm not doing any assumptions. But in the following, at some point I will put lambda over the 1, so it will be over. We will see that it only enters logarithmically with lambda, with the mode divided by v. Okay, so this is a phi. Okay. So yeah, okay. So yeah, v. Okay. Yeah, because I'm putting in terms of. So the equation of motion, I stated this equation, the equation of motion have a solution. I can find ansatz of the solution, of the equation for a solution that looks like phi of z, okay, of x and y if you want, that is of the kind v over square root of 2 times some function only of the radial coordinate. So here I have my tildes, okay, because I'm writing in terms of this tilde coordinate, times e to the I theta. So where x and y and those, theta is the angular variable. So this theta in particular is basically the arctangent of y over x. So it's not really the axion field, but okay, it's the angular variable of this of my system of coordinates. Okay. So I can find ansatz for this equation, and I guess some equation that looks like f second plus f prime over r tilde and so on, minus f 1 over r tilde square. Okay, this is okay. I just plug this ansatz in, and I get plus f tilde f square minus 1. It doesn't really matter, equal to 0. So I get if I plug this ansatz inside my equation, my equation of motion, I get this equation for f. So, but as you see, this ansatz basically will basically find a for this function f. So, and I have to require some condition. So I need to require that f of r goes to 0 for r goes to 0, and then f of r goes to the vev, which is 1, for r goes to infinity. So let me picture it. So if I solve that equation with these boundary conditions, I cannot do it analytically because okay, this is f second plus f prime, because it's not linear. But I can do it with Mathematica, and my solution with these boundary conditions exists first of all, and looks like this. So this I have r tilde, which r times mr to the minus 1 times mr. Okay. The solution exists and looks like this. So the field indeed goes to 0 at 0. In particular, it goes to 0, let's say, like times c times r. Okay, c times r tilde. Okay. So it goes linearly to 0. And then at infinity, it goes to the VEV. But okay, and when you change to order 1, it's basically of order 1 in terms of these coordinates. So my statement is that if you can find a solution of this kind. So how does this solution look in field space? Well, it looks like a string because so this mr times r, which is a tilde. Okay. Yeah. So here I have my z-axis, then I have x and y. So what I'm doing here, the solution looks like the following. Here I have my Mexican hat. So as you see, in the z-axis, so at r equal to 0, basically at z equal to 0, the field is at 0, meaning that the complex scalar field is at the top of my Mexican potential. So here there is a region of size of order mr to the minus 1, okay, in physical coordinates, where the field is on top of the potential. This is just because this stuff goes to 0 and at 0. And as you see, around this axis, the angular variable goes from 0 to pi, then to pi, then to pi in this way, just because I have e to the I theta. And the fact that it goes to 0 is sort of obvious why you should do it, because theta is not really defined in the z-axis, so when x and y goes to 0, just because you have a branch cut of this function. So when it goes to 0, this arctangent of y over x is not well defined. Okay, so in order to solve this singularity, you have to impose that the field goes to 0. So long story short, this solution looks like a string, a line of points along the z-axis, where the field is at the top of a Mexican potential for a size of order, a string core. This is called string core of order mr. String core, and with size of order mr to the minus 1. And in the meantime, the field goes to the at infinity. So at infinity, the field plus or minus infinity. So here and here, which is very far from the string, it goes to the VEV. And in the meantime, the field wraps around once this Mexican potential. And the configuration is called global string, so axion string. And these are known solution, of course, in this field theory business of U1 symmetry breaking. Yeah, that's the next step. So as I was about to say, these configurations, contrary to the axion waves that we saw before, in fact carry a lot of energy density. Yes.
This is just one solution.
Yeah.
There are many others.
I mean, this is one solution. Then you have a lambda solution that they look like loops. They look like like strings that are not really straight. And there are strings with some n here, so you can write multiple times the fundamental domain. But I'm just doing the basic thing also because I'm already late. So just want to the energy of the string is measured via the so-called string tension. So which is basically the energy of a string per unit length. So I take my string and then I'm looking basically at the energy that is stored in a plane that is perpendicular to the string. So this is energy per unit length. And famously, this energy is infinity. Even the energy per unit length is infinity. So this equals infinity. No, well, it's equal to infinity, but now we do a bit more. So this energy is given by the integral in the r times r, and then I have the integral in the theta. So this we integrate in the x dy, in this plane, then from minus pi to pi, and from 0 to infinity. And and here I have to do something like the Hamiltonian, which is stuff here, the gradient square plus the potential of phi. Okay, so I'm not actually going to compute this exactly, but I'm just going to tell you what is the important part that leads to the divergence of this quantity. In particular, the divergence comes from the fact that in this gradient term, I have so if I write this gradient term in terms of my angular coordinate of my cylindrical coordinates, I get 1 plus r plus 1 over r d theta. Okay. No, you have okay, this is the cylindrical version of the gradient. Then I have to apply this to my ansatz, which is okay. Maybe there's a v square root of 2 in front, and then I have this my f of r. Okay, I forget the tilde for now, and e to the I theta. So in principle, this gradient contains also this term. Okay, is this term square, modulo square. So you see, when I apply the derivative of r here, it's more or less fine. But the problem is when I apply the derivative of theta to the e to the I theta, because if I apply the derivative of theta e to the I theta, I get something like v square over 2, no, a term, okay, v square over 2 times something like f squared times 1 over r squared. So because I apply to the theta, I get okay some I that then goes away when I do the modulo square, and on the other hand, then I remain with this f of r like this. And importantly, there is a 1 over r squared here. Okay, and then there is an r. There is an r in front. No, so indeed, so this goes like basically f of r divided by r. So in the end, the integral goes like integral this like this. But importantly, f of r goes to 1 at infinity. So remember, this f of r goes to 1 in order to be at the vev, and we want to be at the vev at infinity. Otherwise, the energy is completely infinity. No, so at least I have to require that it goes to the vev at infinity. Otherwise, there's no chance that the energy is finite. So this f of r goes to 1 at infinity. Goes to infinity, and this corresponds to. So even if I assume that, still this goes like d r over r, and this you know that d r over r is infinity. So I add the version of my energy because of this gradient. So this is to the fact that the axion gradient, so the gradient of the axion field is not vanishing at any okay, it's always basically constant, and is never vanishing at any distance from the center of the string. So at any distance, I get this axion gradient that contributes to my energy density. And if you do the calculation properly, but okay, you can also see from here. At the end, the string tension is given by pi times v squared times the log of r tilde max, and which is basically r max, okay, r max times mr. So what is that term? Well, here I actually I put a IR cutoff here because otherwise I get infinity. So here I put a IR cutoff max. So in this case, I'm integrating basically my energy not up to infinity, but to a certain point max. So I have a logarithmic divergence of the energy. In particular, the string tension looks like log. Looks like the log of the maximum distance I go from the string time divided by the string core. So this is an important formula. Mu is given by pi f squared, pi v squared times log of the R max, if you want, divided by mr to the minus 1, or equivalently mr over R max to the minus 1. So you can say, okay, this energy is infinity, so I can't do actually anything. But in fact, in a realistic configuration, in a realistic universe, you never get only these three strings, but you get a combination of strings that is not really straight, and also some string loops. And in the end, in the early universe, so early universe, this is just a configuration that does analyze. You instead you have a number of configurations. In particular, you have configurations of the kind, for instance, a string that looks like this and a string that looks like that. You,
You subtract like the vacuum solution, which would, does that not make it?
what you mean?
Like you right, like the reason the divergence is because f of r goes to 1 to infinity, right?
Yeah.
But even without the string, f of r goes to 1 to infinity.
But you don't have that gradient, no. In the you have the gradient of the theta angle, this theta parameter, this theta variable. It's very range. Indeed, that's okay. But okay, still, so if you really have a yeah, it's indeed for us to say this is the same as what happens to a charge wire in electrodynamics. So also that one is log divergence, and you also for that you get a cutoff. Yeah, yeah. For that you have a physical cutoff in general in your system. Also here you have a physical cutoff because in general you so for the people who came later, I'm just saying that there are field configurations of the axion. They look like cosmic strings, called axion strings, where they look like lines where the axion goes around from 0 to 2 pi, 2 pi v, no, and they store some energy. They store some energy in them that is logarithmically divergent. Okay, and this is important in the so-called positive scenario. Okay, anyway, so in the early universe, I I guess strings of all the kinds. In particular, I have strings that have the opposite orientation. No, I have configuration that goes like this, and configuration like goes like that. For instance, here the axion wraps the fundamental domain in this way, and in this other way. Okay. And if you do this configuration like this, this configuration is in fact finite. In fact, this configuration is sort of equivalent to a plus charge here, a minus charge here. So per se, they have infinite electric field, but then into dimensions. But then if I go far apart, so the electric field goes to zero. So the electric field energy goes to zero. So singularly, they have infinite logarithmically divergent electric field energy, but in a couple, no. And the idea is that if you take two of these, then a distance far from these two strings, these axion gradients start compensating with each other. So the axion gradient that coming from one string is compensated by the axion gradient coming from the other string. So axion gradient compensate. And in the end, instead of getting okay, if you do the second equation but with 2, you get instead of the R over R, you get the R over R to some higher power. And in the end, effectively, the string tension is given by pi v squared times log of basically the distance divided by m_r minus 1. Okay, so basically the distance of two strings with opposite orientation divided by the size of the string core. Okay. This is just to say that, okay, and then you can also form string loops where around here still the axion goes around from 0 to pi, 2 to pi, and so on. And also these have energy that is have a string tension that is basically to the radius of the loop, which is about the which is also the typical distance between this and this. So you have after the Pecho-Quinn phase transition, in principle you expect that you form these field configurations just because of randomness. So the axion will end up in different points, and by randomness you will get the field configurations. And these field configurations are intrinsically nonlinear, and the evolution basically matters when calculating the dark matter abundance. And this is basically the topic of active field research that people are still doing. And calculating the corresponding the dark matter abundance that arises from the decay of these field configurations is important because it will give me, if you want, the value of the abundance function of a phase, and therefore I can predict a phase, okay, to get the correct dark matter abundance, and so I can measure can measure the action in my experiment with FA. Okay, so this scenario is predictive and motivated to do this calculation. So now I don't want to bother you too much with the details. But the idea is that this is the chronology of our universe. So let me show you here. Here I have temperature, okay, 1 over temperature. So what happens is that at temperatures of order V, okay, you have this Pechequin phase transition where a configuration of these axion strings form. Very, very complicated configuration where there are strings of all the kinds. And then at some point, these strings evolve over time in a very complicated way that follows the equation of motion of the Lagrangian, okay, where I neglect the axion potential. So it forms and it solves the equation of motion, classical equation of motion. And in principle, these are the main problem. So if you have enough, if you have a computer, you can do it. And then at some point, a temperature that will avoid the lambda QCD, that they call lambda, when the Hubble parameter is of order of h star, which is the axion mass, no? Remember, with this parameter h star when the potential was where the Hubble is equal to the mass, where in the pre-inflationary scenario, the axion will start oscillating around the minimum width potential. At this point, I cannot really do anymore that thing because I cannot neglect the axion potential anymore, because the axion potential in this case, like in the pre-inflationary scenario, became cosmologically relevant. And it turns out that at this point, the axion strings are not anymore good solutions. And what instead is a good solution is the axion string connected by two-dimensional surfaces that are called domain walls. Okay, domain walls. Domain walls that are basically solutions of that equation of motion, including the axion potential. In particular, the domain walls are surfaces where the axion field is on top of the axion potential that became cosmologically relevant at this time. Okay. Okay, it turns out that depending on whether n is equal to 1, this number of heavy quarks charged on Pechequin is equal to 1, or n larger than 1, then the dynamics of the domain walls is different. So in this case, they decay, and in this case, instead, they don't decay, they're stable, and the scenario is ruled out unless you introduce other source of Pechequin symmetry breaking. Anyway, the idea is that at this point, the strings don't evolve anymore without the axion potential, but you have to consider the effect of the axion potential. So the idea is that from this point to this point, the strings evolve in a non-trivial way. So you have, for example, a loop that starts shrinking under the effect of this tension because it wants to minimize the static energy, if you want, evolves. And then in way it evolves, it converts the energy that is in the string tension, in these axiostatic gradients around the string. This energy is converted into excitations of the axion field, basically of the angular variable of my Pechequin field. So strings evolve, they minimize the energy, and they emit excitations of my Pechequin field that are called axion waves. These are initially relativistic waves, and then at this point, when the axion gets a mass, they become non-relativistic. Yeah, so you anticipated me. So usually the loop, okay, what people say, the loop decays in a time of order the radius. So time of order radius, the loop starts shrinking, and maybe it oscillates a bit, and after this time they decay. So in only one Hubble time, if you want, the string configuration looks completely different because the loops have decayed. In addition, there are also long strings. No? There are long strings that straighten up. No, there's long strings that stretch over many Hubble patches, and they straighten up, emitting axion waves, or emitting these excitations of the axion field. Yeah, so if you have exponential expansion, so if you have inflation, what in fact happens is that strings might exist before the beginning of inflation. So you have these strings. However, inflation basically stretched exponentially a point here, and so the strings, quote unquote, get exponentially diluted. So that's what people solve this problem, and also how people solve the so-called monopole problem, and also other problems, domain word problem. They just have a okay. In fact, if you have inflation, they go infinitely far apart. Okay, very large far apart. So what? Yeah, but okay. Usually it's not the case in the. Usually you have. Okay, I don't want to bother you too much with the details, but the idea is that it looks like hopeless now, no? Because I have a very complicated field configuration, and I have to solve a nonlinear equation. However, it turns out that from this point to this point here, there is something called the string scaling regime, basically where the configuration looks, so the strings decay, emitting these axion waves, and the configuration looks self-similar. In particular, there's an attractor in the evolution where the number of strings per double patch is approximately constant. So let me delete this part. Yeah. What's the rule? Yeah. Well, in the end, what matters for my discussion is the fact that I have a logarithmic divergent energy density per unit length, energy per unit length. So if you start modifying the Lagrangian that I just deleted, you could probably modify the UV degrees of freedom, but you don't really modify the axion. So this UV divergence really comes from the fact that the axion winds around. So you can modify a bit the UV degrees of freedom, but they just change a bit what you mean here by MR. There will be more complicated matter. But this enters with the log, so it doesn't really matter much. However, you guys are making too many questions, and I'm going way too slow. So long story short, so now in principle you say, okay, just put in the computer, but the computer doesn't help you too much. Okay, that's somewhat, but not too much, because there is also a large ratio of scales in the problem. Because in the problem, I have a string with the size mr to minus 1, which is my string core. And then at the relevant time, which is at this time h star, now when Hubble is equal to h star, the strings will have a typical distance of the order of the Hubble scale, because I told you that the typical distance is of the Hubble scale, and the typical size of the loop will be of the order of Hubble scale. So h minus 1. Because, okay. And you see, if I put if I calculate the ratio between, if you want, this distance h to minus 1 divided by mr to minus 1, so basically the ratio between these two scales, that is usually, okay, this is of order like 10 to the 10 or even more. So if I want to do it in a computer, I will have to resolve both of these scales. I have to have a large number of grid points, no, where I resolve both the scale mr to minus 1 and the typical distance. So I need the 10 to the 10, in principle, cube points to resolve both scales at executive transition. And this is not possible. In fact, user simulations have at most 10 to the 3 to 10 to the 4 cube points. Okay, so this is really a hard problem to do it like by force, and you have to be a bit smart. So this is why still uncertainty on this stuff. So the strings, they format at the Pecho-Queefeld transition, and then they evolve in a so-called, as I say, in what I was calling scaling regime. So the idea is that although the strings are stable if they're taken alone, when I take it together, they can interact with each other. So initially, here will be my upper parameter, -1. This is the size of my universe at this time. There are strings. So I just show them like this. Okay, there are strings. Then, okay, this, of course, this is a very specific configuration. And as time goes on, the strings start interacting with each other. They maybe form loops, they shrink. But in a very peculiar way, they do it in such a way that the number of strings inside the Hubble patch is more or less constant. So here I see I have one of these wiggle per Hubble patch, but my statement, and it is actually shown in numerical simulations, is that as time goes on, there's still more or less the same number of strings per Hubble patch. So this is always my h-1. And then as time goes on again, my Hubble patch becomes much bigger, and I still have a single wiggle in my Hubble patch. Okay, so this is parameterized via a scaling parameter xi that measures the number of strings per Hubble patch. Okay, per Hubble patch per Hubble. Basically, this is defined to be, okay, very roughly, if I have my Hubble patch like this, okay, this is my Hubble patch. This is defined to be basically the length of the strings in one Hubble patch, units of a Hubble radius, averaged over all the Hubbles in the universe. So for instance, this configuration here, I have a Hubble patch and only one string, like this, straight. This has xi equal to 1. Okay, I am simplifying anything, but there's a factor of 4, but the idea is that this configuration xi equal to 1, this configuration instead with 2 have xi equal to 2. Okay, the one with 3 will have xi equal to 3, and then of course I can have like stuff like this at xi, which is not 2, not 3, like it's some number. But the idea is that this measures the density of the strings in one patch, and the strings are measured in units of the Hubble radius in the patch. So, and my statement is that in the scaling regime, xi is approximately constant. So, although the strings decay, they decay, but in such a way that they maintain this constant in the evolution. These are numerical simulations, and the intuitive reason why it's like this is that if there are too many, okay, this is just intuitive. Suppose that you have a lot of strings in your Hubble patch, then they can find themselves very easily, they interact, and in the end, you remain with other one. On the other hand, if you have many Hubble patches, okay, and only one string, so they're very disconnected from each other, they are basically frozen, they cannot find themselves, no? And in the end, what happens is that the Hubble patch increases, like the moving Hubble patch increases. In the end, at some point, they will find themselves. And in the end, you will find yourself again in this situation with only one string of Hubble patch. So this is also called scaling regime. Okay, this is an intuitive reasoning. It's not like we're proving it. And in the end, irrespectively of whether you come from an under-dense configuration or over-dense configuration, you get the same number. So indeed, what we were shown, and here I'm involved, like this new stuff, is that you can calculate this xi as a function of time, as a function of log. Okay, usually you show in log of time, no? So 2 log, okay, is also known as log of mr over h. This is a standard notation. Basically, log of time times fa, okay, normal, okay, or times v, okay. If you have n equal to 1, it's times v. And so here, in a simulation, in principle, you have to go from this to 1 to increase the log of this famous 10 to the 10, or 10 to the 10, which is around 65. Okay, so this would be, in principle, I have to do the full evolution from the Pecho-Queefeld transition, where it's more okay, where this is more, okay, this is in fact 15, but never mind, but I do evolution from there to here to there, no? And what in principle, what actually people can actually do in simulations is only study the evolution up to some point, which is when this is about the 8 or maybe 10. And what we and other people have shown is that in fact, here there's one, in the end, the number of strings goes to more or less the same value, irrespectively to the density of the string. So you form a string configuration initial conditions, and irrespectively of the number of the density, it goes to the same value. And it's still okay. There's still matter of debate, but the idea is that some people, including us, we find that the number of strings, in fact, does not really go to a constant. So it's not really a constant, but in fact, very well approximated by a single log. So even the number of strings increases with this log of time. So in the end, if one does the extrapolation at the physical point, which is at the Q transition there, then you will find a large number of strings. Okay, but anyway, the standard law is that this number goes to a constant, independently of the initial conditions. However, the majority of collaborations find that this increases with log, and this you can think intuitively by the fact that the strings become more and more heavy, more heavy as time evolves, because their tension is logarithmically higher. Okay. So this is what people find. So these are actual simulation data. So we have simulation data that show this. So simulation can study until 8 or 10 maybe, but then one needs to extrapolate this number of strings level patch up from 1 to 10 to 8. So maybe from 3 or 4 to 8. So there's maybe a factor of 5 in e-folds of log of time. Okay, so this is one ingredient that in principle needs to calculate the dark matter abundance in this post-inflation scenario. The other ingredient, if you want, is the actual number of actions produced. So the idea is the following. So while these strings evolve, they emit energy. So they lose energy. Okay, I repeat again, they have some gradient of the axion around. The gradients of the axions, these are axiostatic gradients, so literally gradient of the arc field. Then they start merging with each other. These gradients get converted into gradients of actual waves, so axion waves. Okay, in the end, these axion waves can propagate, maybe they don't emit any more string, they're there. They're relativistic when they're emitted, because initially there's no axion mass. So I'm below this time t star, before this time t star where the axion mass was relevant, so these are relativistic. And I want to understand how much energy is actually emitted, and in these waves, and I want to understand how much is the number of corresponding number of actions emitted. And this can be easily done if you assume, which is proven by proven numerically by simulations, that you have this scaling regime. So if you have this scaling regime, then in fact, you can basically have an analytic argument that calculates for you the energy density of the string of the axions emitted. So suppose that you have a system of free strings. Okay, first of all, let's consider a system of free particles. I have free particles. So if they're free, it means that they're constant, like the position is constant in co-moving coordinates. The universe just expands. Okay. The universe just expands, and they stay constant in co-moving coordinates, meaning that the energy density, if they're free, goes like 1 over scale factor cube. No, okay, we saw last time. If instead you have a system of stuff that is not particles, but they're like strings, okay, the energy density goes as 1 over r squared. No, because you are increasing the 3 spatial dimensions, but in fact, one of the 3 does not redshift, because the strings are basically in one dimension don't redshift. So this is how the energy density of a system of free strings decreases. If you add domain walls, so if you have like surfaces, then the energy density will be 1 over r, because only one direction that shifts. Okay, this is not important, but anyway. So just say that if the system of strings were free, its energy density will go down like 1 over r squared. Then in principle there is also some mu, okay, because okay, of course proportional to mu. However, the strings are not free. They interact with each other, they form these loops, and they shrink, they emit axions, and they go into the scaling regime. And what is the energy of the strings in my scaling regime? Well, to calculate the energy of the strings in my scaling regime, what I have to do, I have my Hubble patch, and then I have my strings. So the energy in the scaling is something like, well, I have my mu times h to the minus 1. So because h to the minus 1 measures the length of the Hubble patch, then mu measures the energy per unit length. So this will be the energy, no? And the volume will be the Hubble patch itself, no? This is the volume. So the energy density as energy over volume. The energy is energy per unit length times the length, which is a Hubble patch, and then this is the volume. Okay, and then this is only if I have one string. If I have many of them, then I have to multiply this by xi. Okay, so that's, and okay, if you do so the Hubble is basically 1 over 2t, no? And if I plug this in and get t squared in the denominator, okay, and in the end this is basically xi mu over t squared. No, the mu is from here, the t is because I have the t. So this is okay, and the free string goes like mu over t, because t squared r goes like t to the 1/2 in the denomination. So as you see, the energy of strings in my scaling regime goes down faster than the energy of strings if they were free. Meaning that the difference in energy, in this case, needs to go into axion radiation, into these axion waves. And in practice, one can, so what one does to calculate the corresponding rate of energy emitted is the following. Well, one very simply considers a configuration at a certain time t0. So I consider a certain time t0. Okay, maybe I deleted something that I shouldn't have deleted, but okay, remember that there was this plot where xi is sort of increasing, like log. So this was xi in his log of 2t times fa, and xi is something like 0.25 times 4 times log. Anyway, so what I do now, I consider as a certain time t equal to t0, okay, t0, a configuration of strings. And then I say, okay, what happens to the configuration of strings if it's free or if it's in the scaling regime? Okay, if it's free, as I just told you, its energy is something like rho free is something like psi of t0. Okay, I allowing myself also some events of t0 because from this divided by t0 t. If it's the scaling, from the formula above, I get psi of t0 mu of t0 divided by t0 squared. Well, okay, this will be at the time t0, then okay, as time goes on, it goes like t squared. Okay, so at time t0, these two are the same, no? Because I get the same stuff. But at time t larger than t0, this one redshifts like the free one, and in the scaling, this one redshifts as the scaling one. Okay, okay. You probably can also forget the dependence here from t. But the idea is that because the most important dependency is from this t. So at time t0, these two are the same, but at larger times, this is different. And basically, what I have to do to calculate the corresponding emission rate is to at time, okay, at a certain time, at time t0, if you want, is to do rho dot free minus rho dot scaling. Okay, this is free. Okay, calculate if you want. Okay, and then I have to replace this t0 by t, no? Some t. So in other words, I'm taking a time t0 configuration and saying, okay, if it's 3, it goes like this. If it's 3, like that. I calculate the instantaneous difference in energy density, and this gives me the what needs to be emitted at that instantaneous at that time to be permit time to be in the scaling regime. And if you do this calculation, okay, this is very easy because if I do dot 3, I get minus something like minus 2 over t. No, if I do dot scaling, I get okay, maybe minus 1 over t times something. No, from this stuff. Here I get the same stuff times 2. Okay, let me. Well, it's you get basically t cube. Okay. Okay, this stuff, okay, it's not really the same, so there's another thing, but okay. The idea is that, okay, maybe I can even write it properly. So it's like minus psi mu over t squared t0 plus 2 psi mu over t cube. Okay, then I have to evaluate this at t equal to t0 equal to t. Okay, and this basically gives me the famous psi mu over t cube, which is also in the discrimination 8 psi 8h cube psi mu. Okay, so long story short, by comparing configuration of free string with that of strings in the scaling regime, I can just say that in order for the scaling regime to be maintained, to have this constant number of strings over volume, I need to lose energy from my configuration in this way. And this energy needs to go into excitations of the axion field, or if you want, of the radial modes, but mostly goes into the excitations of the axion field, because that's the basically almost massless degree of freedom. And then it's done now, because in principle, mu, you know, mu was pi v squared times this log, calculated at this time, which is basically 65, no? V is a phase, you know, okay, it's a parameter, and psi is this value here, which is maybe 15 at the correct time. So in principle, this gives me the energy density at every time, but at the final time and so on. However, it turns out that what actually matters for the abundance is not really only the energy density, but what actually matters is also the spectrum of actions emitted. Because long story short, so suppose that now that you have this string configuration, it emits energies, but it can emit energy in a number of wavelengths. No, you can emit energy in wavelengths that are small or that are large. So I want to do this thing. Sorry. This is the rate of energy emitted from strings. So energy density, in principle, density, for maintaining the scaling regime. So to maintain a constant number of strings available patch, because if you don't emit energy, then you will redshift, like the energy will redshift like free. Okay, it needs to be lost. Like you need to take it away. So you just increase linearly. So if you know, if in this case we would increase psi, so psi would, so if it were free, psi would be proportional to t. So you start having more and more strings inside your volume. So to get rid of the strings and the corresponding axiostatic gradients, you have to emit energy. So if you want, you have to convert. So if they were free, the Hubble volume will have more and more strings. Okay, and psi would increase linearly. But then you have to deplete these strings, and you deplete them by emitting axions. Okay, I don't want to bother you too much with this. Yeah. Yeah, so in this case, the radiation, this case is lower. Yeah. The radiation module, the fact that also mu depends a bit on time logarithmically via this. Yes. Otherwise, it would go slower, goes lower than radiation. So it's like having a dark sector where you have something that goes like matter, if it was free, but since it would dominate, okay, this would dominate. So you have to, as time goes on, you have to make this dark sector decay into something else to have like to where the energy goes like radiation. This something else is basically the same field, which is the action waves. Yeah, so yeah, may say there is the fraction of energy density of the universe. At this time, completely negligible. The same thing as the pre-fission scenario. In pre-fission scenario, before material equality, the energy density of the axion was negligible. Only on material equality becomes over the one. Okay, becomes over the one half of each point. Okay, so we need to. Okay, we have this energy emitted from strings into action waves. So during all this period, you produce these action waves, were red, produce action waves. So the number of strings is more or less constant per volume. Okay, our volume increases, of course, and energy emitted into action waves. And I'm here now, and I see a bunch of action waves emitted from all the previous times. And my question is, well, at this point, the actions become non-relativistic, so I want to compute the corresponding number density in a string of actions from strings at this point, T star, when, as I said, the actions become non-relativistic and they start redshift like matter, is when in the pre-inflation scenario, the action starts oscillating around the minimum with potential. So to do that, well, to calculate the number density, what I have to do, in principle, I have to do the following. I have to take the integral. Okay, what is the number density? Well, number density in a string will be basically for each momentum k, I have to divide 0a in respect to omega k. Omega k will be square root of ma square plus k square. No, and this before this T star is approximated by simply k, because ma is more than k. Okay, the typical momentum, which is over the Hubble. Okay, so this is all this, and then okay, I have to integrate over all the momenta that are emitted. No, this is the integral in this, which is also like 0 k, 0 in the k, okay, 0 in the k times 1 over k delta k. So this means that I have to actually know what is the spectrum of actions emitted. So you can think that these string configurations emit wavelengths of all the typical size, no? So the spectrum of actions emitted, now I make it a bit brief, but the idea is that as the strings interact with each other from loops and so on, they emit some wavelengths that you can imagine to be of order, no, of the typical size of the string itself, no? So the string was more or less of order Hubble to -1, so the wavelength will be more or less of order of Hubble to -1. And this is usually written in terms of the gamma in decay. So the gamma in decay is defined to be such that the integral in decay of the gamma in decay is equal to gamma. So this is basically a function of t and k, and it's only a function of t. No, this is basically the momentum distribution of my emitted actions. And, okay, the gamma in decay has this form. So sorry. Okay, and is related to this the line decay. So as I said before, given that you expect the ultimate wavelength or moment of the Hubble is the gamma decay, is supposed to be peaked more or less at Hubble. In particular, there is a coefficient that maybe is over the 10 in front of it that I call x naught. Okay, and this Hubble. And then, okay, just because most of the wavelengths are emitted, went over the Hubble. So here you have Hubble. This is a wavelength. The wavelengths I should show them in red, and then the strings emit them. Okay. Okay, this is a peak. Okay, and then there's a cutoff at a smaller momenta. Then there's another cutoff at large momenta that is of order of MR, or if you want FA, if this or V, no, if this lambda is over the 1, the quartic coupling, because basically the smaller scale, most of the physical scale, the problem is MR itself. Okay. So in between, so you cannot emit stuff that is more UV. So this very a UV scale is a very small scale of order, like one much more than a proton size. In between, there's no more scale. So usually people parameterize this as 1 over k to the q, a single power law in between. Yes. Determines the hardness, quote unquote, of a spectrum. So if q is larger than 1, then the spectrum is IR dominated. If q is equal to 1, then it's scale invariant. Okay, invariant. And if q is smaller than 1, is UV dominated. Because if it's q larger than 1, imagine infinity, so there's a big peak at momenta over the Hubble. So basically all the wavelengths are emitted momenta over the Hubble. If q is more than 1, then there's a long tail. So most of the energy is emitted in this UV momenta over the MR. If q is equal to 1 instead, well, you have a basically scale invariant spectrum. Okay, if you multiply by k, you have a scale invariant spectrum. And long story short, it is this number of q that determines the number density, because you can plug in the gamma in decay inside the. Okay, let me write it here. This is my next. This is my next topic that I want to say, but it's from simulations basically. You have to solve the equations of motion in a simulation. Okay. Q is, I mean, the different schools. People say that some people say that Q is equal to 1, and some other people say Q is larger than 1. But I am of the school of saying that Q is larger than 1, because if you have a string loop, the string loop starts decaying into a smaller loop, and then maybe it bounces a bit, and then it decays completely. While doing that, the only scale in the problem is more or less the length of the loop at initial time. So when it does this, you go into wavelengths that are always over the string loop, especially if it oscillates many times. In fact, in this limit of smaller string core size compared to the string loop size, these strings become almost local strings, and the local strings basically where the action is more and more decoupled from the string itself. These local strings are, in fact, oscillate many times, and these emit gravitational waves in principle, because you don't have any more reaction. But the idea is that when they oscillate many times, they emit wavelengths always of the initial time, of the initial string radius. Meaning that, in this case, you have a delta function here. This is, in fact, a delta function. So Q is equal to infinity, okay, much larger than 1. In fact, it's infinity. There are other schools. So this school is, the one I just said is from Shellard in the 80s. Shellard plus in the 80s, in the 90s maybe. And other schools that say that, in fact, the spectrum scale invariant. You made all this wavelength, but also at the same time, also the wavelengths are all the scales from this to this one And in this one, you have is Q equal. Q is more than 1. Nobody actually claims this, because in this case, the spectrum will really depend on the UV completion of the theory. Okay. So, but okay, what people actually do, so is actually do simulations. Like we did simulations, also other people, and they calculate the spectrum that indeed looks like this at some time, maybe when this log is over the 6.5 or so on, and so. But then as time goes on, the spectrum sort of changes. Y-axis is my d gamma in decay. Sorry. So this is the same thing as here. And as time goes on, some people see, including us, a change in the spectrum. So initially, this corresponds initially to Q. So if I show Q as a function of time of this log, initially this corresponds to Q, let's say 0.65. And then as time goes on, these points increase. So it's from, for instance, from 6 to maybe 8, or 5 to 8. We see a non-trivial dependence of Q. So if the spectrum becomes more and more IR dominated, if you want. And an extrapolation, a conservative extrapolation would tell you that Q at some point becomes larger than 1. However, in the simulation, we always see that this, at least for the data that we have, we always see that at most at 0.95. Although some simulations even show larger value. The other people who instead see that okay, they have much larger error, but they have points that are distributed like this, and they make the statement that in the end Q is equal to 1. So here is still open debate, and okay, everybody thinks they are right. In particular, we think we think we are, but still open. So it's still not known whether in the end the Q is equal to 1 or larger than 1. And
How do you know that it's not smaller than 1 again?
well, it's more than 1 in a simulation. No? This goes from 65 to 95.
Yeah, but it gets stuck at 0.96.
Well, you have to do an extrapolation. Yeah, here you have to go to 70, no?
Yes, but
So
you know that there's no, right?
no, you theoretically you don't know. You have this, the only thing here, you have this argument. You have this argument that eventually the string loops will oscillate infinite number of times, because as the string thickness goes to 0, you cannot emit any more actions, because basically you have a mismatch of scales. So at some point we know that the string loops should oscillate, and well, and we expect that the only wavelength that you can emit at this point is over the Hubble. So at some point you might emit only long wavelengths, so Q equal to infinity if you want at this point, maybe. But we really have still open debate. But okay, just wanted to show last formulas showing that how the number density from strings depends on Q. Okay, now I told you all this boring story that you emit some waves with some frequencies, and maybe you have some spectrum, some momenta. I also calculated for you I will write it here, gamma is 8 psi mu h2 minus h cube. This will be the energy density emitted from the strings to maintain the scaling regime. And the idea is that I have to plug all this information inside this formula. In particular, this Didoni decay will depend on this gamma, the evolutionary gamma. So I had to do the integration of all the energy density emitted from the initial time to the final time with this spectra. Okay, so you can do it, and in the end, it turns out that a good approximation of that number density, and is also intuitive. No, this number density is basically the average momentum times times the emission rate. So the idea is that this number density Na is over the average inverse momentum, no, times gamma times h to minus 1. Okay, this will be the energy emitted in the last Hubble time. Okay, and then okay, this will be the energy density emitted in last Hubble time. Energy density last Hubble time, last Hubble at t, let's say, when at mt. So this one I will eventually have to evaluate at t equal to t star, no, when the axons start becoming non-relativistic. So this, I think for all of them, and this this k to minus 1. Well, depends, no, on whether, so k to minus 1 is okay, is over the x naught h naught to minus h to minus 1, no. So in this case, intuitively, the average inverse momentum is peaked at the peak, no, because you have only, we can do it, of course, properly, but it's peaked at here. Here instead, given that you have a scale invariant spectrum, you have something like 1 over the log of mr over x naught h. So here, instead, the average momentum is basically some geometrical average from this and here. So is a bit in between. Okay, is factor 1 over 70, maybe smaller, or 75, 70 smaller. So this is 1 over, okay, this is the average momentum. So the momentum is larger, no? So momentum is larger. So let me, okay, so I think it's like this. Momentum is larger, so the inverse momentum is smaller. And then in this case, you have like something like mr. So the momentum is much larger, so you have h naught. So okay, is the mr, basically mr. The average momentum is here, is inside here, is inside the UV. Okay. Okay, and if I plug in, so now I have to plug. What I have to plug, I have to do NA at T star, some string. I have to plug these different options. So this is for Q larger than 1, Q equal to 1, and Q smaller than 1. Okay. I have to plug these different options inside my formula. So my formula has this gamma that was a famous 8 mu psi h cube, and then I have h, which is h, and these possibilities. If I do that, what do I get? Well, I get that in the first case, okay, I get something 8, okay, at time t star, h star times xi star mu star over x naught. Okay, and then I have this possibility is basically 1 or 1 over this log, or log at time t star, no, log star, no, which is around 17. And then I have simply hx naught over mr to some positive power. So in this case, I get this number. In this case, I have this number divided by 70, is a bit smaller. In this case, I have a number, this is the same number multiplied by something that is much more than 1. So intuitively what it means that this energy emitted from strings can go either into many axions with small momentum, which is this case here, the IR domination. Same energy can go into only a few axions that have UV momentum over the MR or V, okay. However, what actually matters is not really the energy of the axions, because all these axions are initially relativistic, then the redshift, and they become non-relativistic. The number density is dominated by non-relativistic axions. In this case, you have a large number, which is this one, and in this other case, we have a small number. So long story short, remember that last time we said that misalignment number density and a misalignment at this time t star, no, remember, it was something like theta 0 square, and then I have h star square, h star times fa square, okay, or v in this case. Okay, this was the one for misalignment. Theta 0 is the initial misalignment angle. So I add the two and see which one is bigger. So h star kind of cancels. Mu, remember, was something like pi v squared times the log of mr over h star. Okay. So also v cancels, and if I take the ratio, what do I get? Well, I get in the case q larger than 1, in the case q larger than 1 that we believe in, okay, otherwise you have to multiply by over 1/70, basically. The ratio NA string at T star with respect to the misalignment one at T star is something about the 8 pi psi star log star, okay, log star divided by x naught theta 0 square. Okay, so theta 0, okay, is whatever it is for misalignment. X naught is this parameter here that sort of measures, my speaker spectrum with respect to h is order 1 number. In fact, what we see is something of order 10, because you can measure in a simulation, okay. And psi star is something like 15 if you believe this increase, this logarithmic increase of the number of usable volume that I deleted. And log is around 65. So as you see, naively, if you put theta 0 equal to 1, for which, okay, I remind you, for theta 0 equal to 1, you have the corresponding abundance correct for 10 to the 12 GV, FA 10 to the 12 GV. Then, then you see that you have a huge announcement. So despite this, theta 0 is of order 10, this corresponds to a huge announcement because you have to, and basically this announcement comes from the fact that you have a number of strings double patches. This is not 1, but it's 15, so you have a factor of 15. And then you have this log star, basically, on top of the fact that there are a lot of strings, like maybe 15 double patch at the final time here. These strings also have some gradient energy, this axiostatic gradient that contributes with this log star. Okay, if you plug in a number, this is of order, let's say, 2.5, 10 times to the 3, for psi star of order 15, okay, and then log star over 65, and then 10 over h naught, x naught, okay, theta 0 square. Okay, so you have a large announcement. You say, okay, so my calculation before was completely wrong because I have a large announcement of axioms. In fact, this calculation is not completely correct. It's actually correct. This is for q larger than 1. However, it turns out that the axioms that are emitted from the strings are not exactly non-relativistic exactly at T star, but they become non-relativistic a bit after, because you remember, for the pre-inflation scenario, we saw that at time T star, the axions started oscillating around the minimum, and from that point, the axioms were completely non-relativistic, okay, non-relativistic, and also the number density was conserved. So here we are comparing the two, and we are assuming that in both cases, also the axioms emitted from strings that are basically waves become non-relativistic at that point. However, given that there is a large enhancement of the energy density, with respect to the misalignment, okay, just to say, this from Gorghetto et al. 2020, so it's new stuff. Okay. So basically, my energy density from strings, a function of time, this is T star. So the idea is that at the time T star, the axion potential is bounded to be something like ma square, fa square, which is basically h star square, fa square. Okay, the axion potential is a cosine. I remove the cosine, so it's sort of here ma square, fa square. Or the energy density of strings at this time is basically this product here. and is in fact enhanced by a factor over the basically psi log, so it's psi star log star times this, so is times ma square fa square. Okay, so it's much larger. So you, yeah. Hmm? No, the log is like ma square fa square times psi star log star. Okay, so log yes, it's log star. Because you can compute it like so. From this gamma is that thing, then you multiply by h2 minus 1, you get h squared. Okay, h squared is ma square. Okay, at the identity star, and then fa comes from the mu that has a v square in front. Okay, there's also pi if you want. There's a pi. But okay, long story short, given that you have so many actions emitted from strings by this stuff, the energy is much larger compared to the potential. So the actions keep shifting relativistically, while at the same the actions keep shifting relativistically, and this to an energy that doesn't decrease like matter, but still like radiation for a bit until at a later time. So this means that in fact, if you do the calculation properly, the number density, so the energy density that shifts for a bit even after T star, and this implies that this ratio is corrected. So the ratio that I call the NA string over NA misalignment is corrected. Okay, you can do calculation properly, but it's corrected instead of having 8 pi psi log, it's corrected like with a square root. And this, of course, I don't have detail to explain why, but intuitively, okay, let me even without this external, like this. And this just because the actions do not become non-relativistic at this star, but they still keep shifting relativistically for a bit, depleting a bit the energy density compared to that naive expectation. And this is what we say. So this is our so I'm saying this because we actually our paper. And if you plug in numbers, this is a factor of maybe 160 larger. So it's not this number here, but it's the square root. Okay, it's still a bit larger. So it probably is the well. It depends if this is much larger. I think it's still a bit much larger because this. So you have this time this fruit happens every time the energy density in these waves is larger compared to the potential. Okay. Anyway, so now I want to give you the number. Now we go to the numbers because we want to measure the axion mass. So you saw from last day that for theta 0 equal to 1, I get the correct abundance for FA around 10 to the 12 GeV. Okay? This misalignment. For, and now you remember also that omega axion misalignment, okay, omega axion is proportional to FA to this funny power 7/6 because of this alpha dependence. So in order for me to reproduce the correct incremental abundance, I have to, if you want, so FA string, if you want, would be this FA misalignment divided by this 160 to the 6/7. Okay, very, very roughly, no? Because I have to invert the corresponding formula. I get 6/7 because I have 160 more in the density. Okay, this just from this. And this, what I get if I do this is around 10 to the 10 GeV. No? Which corresponds to an axion mass MA over the 0.5 times 10 to the 3 minus 3 electron volt. So long story short, contribution from strings, some evidence that the contribution of the matter mass from strings pushes a bit high the dark matter mass or a bit lower the decay constant. And so we are maybe at the upper edge of the famous plot. Do I have 2 minutes? We start a bit later. So we are at the lower edge. So I have my Ga gamma gamma as a function of a function of MA. You remember we have this famous plot, no, where I have my KSVZ and the FSZ, okay, whatever, and you have 10 to minus 3 here, and maybe we are at the upper edge of here, maybe 0.5, 10 to minus 3. But of course, this, okay, this, if you have q equal to 1, then you have probably to divide by 70. So this log star have 1 over log star here, if q equal to 1. And then this will push this number a bit lower and this number a bit higher. And that's why other people that are different from us, that different group, have a different prediction for the axion mass. This is because there's a disagreement on the value of Q. Okay, so let me finish by saying what happens to the domain wall. So now we have all these axions emitted from strings. And what happens to them? Well, the axions in principle go freely, but on the other hand, I told you before that at this point the axion potential becomes relevant. The axion potential becomes relevant, and as the effect of first of all making the axions massive, these axion waves massive, and the other effect is that they connect the strings with a domain wall. So the string goes from the axion around this. So I'm looking at the string going here inside, and here string going outside. From the axion goes from 0 to pi and so on. So at this time, T star, no, the axion potential becomes relevant, and basically all these points become the edge, okay, or the surface of the domain wall. So if you want, there are these strings, and the points where it is pi, no, where the axion is pi, are at the top of the axion potential. So I have axion potential as a function of A. And this point are 2 pi Fa. Okay, these points are at the top of the potential, where this pi Fa. Okay, and they form a surface that's called domain wall. And the idea is that if n equal to 1, you have only one domain wall, because Fa is equal to V. This is also 2 pi V. So once the axion winds around, you only have one place where the potential is maximum. Okay, there's only one domain wall. And if you actually do the simulation, okay, you can understand it qualitatively. The fact that it is more convenient for the system of strings domain walls to decay under the tension of the domain wall. So the domain wall kind of puts the string together, and the system decays. And this gives another contribution to the dark matter abundance that is still not known. This is completely not known. No, okay, so in that case, the system will decays into more axion waves, and the contribution is basically yet uncalculable, because in the system we have so many different scales. Okay, we have the typical scene distance, which is over the hub, and this is very microscopic. People can do simulations, but when people do simulations, they use completely different parameters compared to the reality, so they're hard to extrapolate. But okay, they might give a contribution that is even larger than the one from strings. It is possible, and as a result, in principle, this 160 can be larger. So this Fa can be smaller, because I can get okay, it can be larger. And so what at the end we say is that Fa is considering the domain wall contribution. Fa can be maybe smaller than 10. We give this bound not smaller than 10 to the 10 GeV, corresponding to Ma larger than 0.5, 10 to minus 3 EV. This is considered the domain wall contribution, because we are completely agnostic. If it's subnominal, if the domain wall emission is subnominal, then then this actual equality. This happens when n equal to 1. When n is larger than 1, in fact, it turns out that you have n domain walls attached to the strings. So let me show it. So you have each string is attached to n domain walls because, in fact, okay, let me say in 30 seconds, what happens is that the period of V is not FA, it's different of FA. So around the string, the axiom sees many minima because it wraps of 2 pi V, but within 2 pi V there are n times 2 pi FA. Okay, so it sees because V is different from FA, and it turns out that if you don't include additional CP violation, these domain walls that attach to the string make the strings. So here I have a string here, it goes inside, the other string here goes outside. And the system of strings domain walls is stable. Each string is attached of each of domain wall. All the domain walls pull the string in a different direction. And okay, basically, once I do that, they form a stable system that is ruled out, and it can decay only if you change the axial potential and you put an additional PQ variating term. And it is not clear that you can put a large enough PQ variating term for the system to decay close enough, early enough in time for the to solve the strong CP problem, because as soon as you start putting PQ variating potential, then you start screwing up the strong CP problem. Okay, in this case, completely unknown. So this, I conclude with this saying that in a post-inflation scenario, you might be in this regime, but it depends on the uncertainty on Q, on the of the emission rate of strings. Okay, so sorry for the delay. Thank you.
Let's thank Marco again for the